Well, good morning, everybody. It's time for part 3 of my series on spherical Earth versus flat. Today I'm going to talk more about distance, and then we're going to have one mind-blowing result. I bet you can't wait. Here is a little background. You remember in part 1, we talked about circumference and tilt, which I proved for 19 different cities from around the world, and calculating the latitude only using solar high noon. Part 2, we talked about distances, and then more about rotation. And I think we clearly proved that the Earth is a sphere and rotating. Here is some of the data from the distances only, and I think you can clearly see that the measured distance that I got off of Google is more closely related to the calculated distance for a sphere than it is for flat Earth distances. It's kind of obvious, and especially in the southern hemisphere. So after I looked at those distances, I thought, some of you guys will say that we just can't trust those websites to give us accurate results. So I needed to find a way that I could validate distances. So is there any way that I can measure distances for myself? So what I'm thinking is I could get some standardized distances and look at them both on a globe map and on an AE or flat map. So for standardized distances, I figure we should use latitude and longitude. I think everybody agrees that those are valid location. So I took the from point latitude and longitude as 0 degrees north and 0 degrees east. So then I wanted 2 points to be reasonably far away from the first point, so that I could be able to measure those. So I chose 40 degrees and 100 degrees. 40 degrees latitude, 100 degrees longitude. And so using those, I can get 4 lines on each map to measure. 40 degrees north and 100 degrees east, 40 degrees north and 100 degrees west, 40 degrees south and 100 degrees east, 40 degrees south and 100 degrees west. And so then I drew lines on the maps with a straight edge. And here's what those lines look like. On the flat Earth map, we have, here's our 4 lines. The 0 point is right there in the Atlantic Ocean, close to Africa. And on a spherical map, here are my 4 lines that I drew. Again, the center point is right there, and then there's my 40 degrees, 100 degrees, and so forth for the 4 line segments. So my first notion was to check those four distances with 5 unrelated web calculators. So here's my 4 latitude longitudes, and so I took these 5 websites and calculated the 4 distances. And of course, these will be spherical distances because of the nature of the calculators. And I get these numbers, which you can see are pretty close to the exact same numbers for all, 20 numbers. I also calculated the ratio of this first number to this last number. I wanted to see, I wanted to use this ratio because we might think that the maps have a different aspect. So that's why I did the ratio to divide out that aspect. Again, here are my 20 measurements from web calculators. This last one right here is Walter Bislin's calculator. First off is the spherical coordinates, or spherical measurements. Again, their ratio is 1. And then the flat earth measurements, and you can see those there, and their ratio is 0.647. Quite different from the one of the spherical map. So on my spherical map, it's called a Mercator map. You can see that, these are my measurements that I did on the map. I got 78 millimeters for every one of those 4 line segments. So the ratio is 1. For the AE map, everyone knows that's the azimuthal equidistant map. And here are the numbers that I got for measuring. And the ratio was 0.685. 0.685 totally matches the 0.647 from the calculator. So I just wanted to show you this because it clearly shows that the website calculator is correct. And you can also see that the spherical numbers are much more, much better than the flat earth numbers. So my last measurement, I wanted to consider the surface areas. So for a flat circular disc, this is for any circle, you know that. The surface area is pi r squared. The usual measurement, there's pi. The radius squared, and the radius I got from the typical number accepted for miles per degree is 69.1, and then of course there are 180 degrees from the North Pole to the edge of your circle. And so the answer for that is 4.86 times 10 to the 8 square miles, which is the same as 486 million square miles. So then for a perfect sphere, any perfect sphere, we know that the surface area is 4 pi r squared. Again, you can look up that formula if you like. So 4 times pi times the radius of the Earth. That should be the radius of the Earth squared. I didn't put the superscript on there. But that's equal to 1.97 times 10 to the 8 square miles, which is 197 million square miles. So that is a considerable difference. Basically, a sphere is half the surface area of the circular disk. So what I'm wondering now, my next question is, can I find some kind of measurement to compare to that? And so the first thing I looked for was an estimate of land area, and I found this website that reports statistics about world countries, and it just happens to include surface area. And here is the website in case you want to go look it up. By the way, they have a limit to how much you can look at unless you pay a subscription fee. So that's the first one. I added in Antarctica because it's not a country. So I added that in. There were 204 countries, from Russia, which was 17 million square miles, all the way down to a small country that was 2 square miles. So it's quite a range of data. So then that covers the land area, but there's an awful lot of water. So I looked up surface areas for water, and I found an unrelated website that gives surface area for 18 oceans and the seas. And there is the website for that. Again, you can look that up. Here is a sample of the data that I used. Again, over here is country and square kilometers. This is the square kilometers, and this is the country name. And then over here is the ocean water areas for all these 18 different seas and oceans, square miles, square kilometers. So that was the data I used. So now if you remember from our previous calculation, for a flat circular disk, the area is 4.86 times 10 to the 8 square miles. For a sphere, it's 1.97 times 10 to the 8 square miles. And then here are the measurements that I got off of the internet for the water, and then for 205 numbers, including Antarctica. So I got 137 million square miles, and then this one is 53 million square miles. Add those together and you get 1.91 times 10 to the 8, or 191 million square miles. So here is my observed data from unrelated websites. My 1.9 or 191 million square miles is almost identical to the 197 million square miles that we could easily calculate for a sphere. I think that's pretty close and tells you pretty much that the surface area of a sphere of the Earth almost perfectly matches what a sphere would be. So let's look at that data again. Here's my surface area of water, surface area of the countries, the land area. The total surface area, remember, is 191 million square miles. One more calculation that I've thought about making is, and we've heard it said over and over, that the Earth's surface is 71% water. So I thought, can I calculate that number? So I calculated percent water, 100 times the amount of water, 137, divided by the total, 191, and I get 71.7%. And you can see those two numbers are virtually identical. This should just blow your mind that we could observe data for the area and then find our exact percentage of water. And all I can say to that is, ba-bam! Blows my mind. Here are my acknowledgments. Don't forget to check on these websites. And these are some more of the websites that I watch, and these guys are top notch. If you don't watch these guys, shame on you. And that's all for today.